So welcome everyone to the third seminar of this edition. Today we have 3 talks. And as always, please reach out to us if you want to also have the slides in PDF format. We will then share it with you. So happy to do that. And today we will have 3 talks. First, Thomas will show us some insights on his experimental setup of his shockwave analysis. Then we will have Markus showing us some geometric sensing concepts for automated construction of Hyperloop infrastructure. And then we will have Alfred showing us some tunneling mega projects and how to plan them and how to actually assess the risks. Thomas, please start, and the stage is yours.
Okay, yeah. Hi, everybody. My name's Thomas. I think I should quickly mention that you can put your questions into Slido. Just go into the webpage or with your cell phone and type in the VAC Transport Seminar hashtag. Okay, yeah. So welcome, everybody. My name's Thomas. I'm a bachelor at the ETH Zurich. I'm studying mechanical engineering and at the moment conducting my bachelor thesis, and the name of the thesis is the investigation of shockwaves in low pressure vacuum transport tubes. And what that means exactly is pretty much summed up in this video. I hope this works.
There's nothing in its way in terms of air because there's a vacuum. And so it bursts out of this side at something over 300 miles per hour.
That's the theory.
Here we go. Whoa! Holy oh man, that was really good. I didn't expect it to work that well.
The 3-foot prototype worked scarily well. Popping the sealed vacuum caused a sudden influx of air, and the pressure differential sends the ball rocketing.
So yeah, that is basically what I'm doing for my bachelor thesis. I'm investigating shockwaves generated through breaches into a vacuum, a LOVA, loss of vacuum accident, and I'm trying to grasp an understanding of this highly dynamic phenomena. This phenomena is a critical safety concern for the Hyperloop concept and one of the main criticisms to Hyperloop. And understanding this phenomena will give insights into dimensioning of Hyperloop structures. For my thesis, I'm simulating and experimentally validating this problem. So breaches into vacuum tubes can happen for various reasons: accidents, explosions, earthquakes, or other causes. And the main question I'm asking myself, as I mentioned before, is what happens inside the vacuum tube when the air expands into it? And how does the breach size influence the resulting pressure wave? So from a theoretical, fluid dynamical, mathematical point of view, it's not a new problem. There's a famous formula, outflow out of a pressure vessel by de Saint-Venant and Wanzel. Everybody who's had a fluid dynamic lecture should maybe have seen this before. It basically states exactly the problem. It shows the velocity profile of a fluid particle experiencing a pressure change. So in my case, or in our case, the pressure vessel is the atmospheric pressure. So the vessel is the atmosphere, and it's an outflow into vacuum. Through this mathematical formula, the theoretical limit of maximal possible velocity, neglecting any areas, inflow areas, showing the P to P0 going to 0, gives for atmospheric pressure and atmospheric air conditions a maximum theoretical value of 750 meters per second. So I'm using a simulation software called Track Relab, and it's an advanced computational engine, usually used in nuclear reactor systems. The software uses finite volume numerical methods and has a component-based approach to modeling these systems. So what that means is that there's a catalog set of objects, components you can choose from, and then build your model. So normally that would be some pipes, then a reactor, turbines, etc. So for my case, it's a pretty simple setup. I have a 1D component called pipe, which is a pipe. And in the simulation, I have a 2000 millimeter pipe with an inner diameter of 56 millimeters. I set this pipe under a vacuum condition, namely 50 millibar. And attached to the pipe, I have a valve, and I can specify in the software the settings of this valve. So the inflow area and the time the valve takes to open the entire cross-section. So using this software, I've conducted some simulations and calculations, and these are some of the results. So I simulate from 0 to 1.6 seconds. So I simulate 1.6 seconds, and the breach beginning at second 1.0. So here, the breach begins at 1.0, and the valve takes 0.05 seconds to open. So after 1.05 seconds, the entire cross section is open, and I have a complete inflow of the air. The tube itself, I'll show the picture again, is made of 200 nodes, counting from the end of the pipe upwards up to 200. So as I mentioned before, inside the vacuum, inside the tube, I have a 50 millibar vacuum initial conditions. So the upper plot, you can see the node number 1, which is right at the end of the tube. This is the maximum pressure occurring inside the tube. What was to be expected, because the air rushes inside the tube, compresses at the end when it hits the wall, and then achieves a maximum pressure of 1.3 bar. Through this compression, we have a change in the pressure differential. So the compressed air pushes backwards towards atmosphere, creating these oscillations with a pretty stable period. So roughly after a half a second of the breach, we have achieved a steady state and achieved atmospheric pressure inside the tube again. So for the velocity, also an interesting phenomena, the maximum velocity appears at node 180. So if I show the picture again, roughly after 20 centimeters of the opening. And the simulation calculates a maximum velocity of 370 meters per second, which is a pretty high velocity. Then similar to the pressures, you can see the oscillations, of course, in a sign change of the velocity, because the air rushes outwards again after hitting the end. And here's an animation of the results from the simulation. So yeah, you can see the first pressure wave coming in quite slowly. That's because the time steps are very small there, and the time step increases with the length of the simulation. So here's the pressure wave hitting the end, reflecting, and then here are the oscillations. So the upper one is pressure, and the lower one is velocity. Maybe one more time. Yeah, it's very interesting to see how there's a nearly instantaneous velocity increase with the pressure wave incoming. So for the experimental setup, trying to validate these simulation results, I have a 2-meter acrylic glass tube. That is also the reason why I use these dimensions in the simulation. It has an inner diameter of 56 millimeters, as in the simulation. There are 2 pressure sensors installed right at the end of the tube, a high-speed camera, and a fog machine. For the pressure measurements, I have 2 sensors. One is a high-frequency piezoelectric dynamic pressure sensor by PCB Piezotronics, and the second one is an absolute pressure sensor by Baumer. They're both located, as I just said, at the end of the tube, where the maximum pressure occurs. So for the velocity measurement, I have 2 approaches, and I'm trying to capture the pressure wave with a high-speed camera, which is not a very easy task. One approach is using the fog machine. I'm creating some sort of aerosol. I can enrich the air in front of the air intake with the fog, and then try to capture the moving particles or the moving smoke inside the tube. And if I don't succeed with that, another approach is using light particles. So similar to the vacuum cannon you saw before, just maybe with smaller particles, and try to measure their velocity with a high-speed camera. But then I would lose, so the approximation would be less good because of the inertia of the particles. So for the breach, the main problem is that the breach time should be identical for every single breach. But for the testing, I want to use different sizes for the aperture. So my idea was using this plug you can see in this CAD model, so the adapter, which is screwed to the tube, and these plates, reducers, I call them. So these plates have different hole diameters and give me the possibility of interchanging the hole size for each test. This results in that the cross-section acting on the plug is always the same. So the force acting on the plug will always be the same from the vacuum. Attaching this plug to a weight, which is being dropped out of a specific height, which is always the same for every breach, allows for semi-identical breach time for every test. So yeah, due to COVID, I wasn't able to manufacture these parts yet, unfortunately. For the moment, I'm using 3D printed parts, which was semi-successful. The black part is not very vacuum proof, unfortunately. And in the next steps, I'm trying to mill these parts out of aluminum. So yeah, the first preliminary tests I was able to run, this was a 20mm breach. On the left side, you can see the absolute pressure, which increases from 50 millibar to nearly 1 bar atmospheric pressure instantaneously without an overshoot. And the second test I did was with a 56mm breach, showing the characteristic oscillations we also saw in the simulation. So the influence of the breach size there's a very big influence by the breach size. As you can see, this test, the 56mm breach, we have an overshoot roughly up to 1.3 bar nearly. So pretty much that's what the simulation predicted. Yeah. Well, thank you for your interest. I'm happy to take in any questions.
Thank you very much, Thomas, for the presentation. Then we go
quickly looking at the time, and we should rush it a bit probably.
Yes.
But yeah, thank you for having the questions, Natalie.
Okay, so one question, is LoVa an official definition? Where does it come from?
So official definition, I'm not sure. I found it on the internet, and it's mainly used in fusion reactors, from my understanding. So the fusion reactors are on the vacuum, and it's also something that was extensively studied in if they have a vacuum breach. So the only papers I found about that.
Okay, then another question: How did you come about using trace track relap? Through research or recommendation? Why not something else?
Mainly because my supervisor works at PSI, and he is in the nuclear engineering department, and the main software he uses is Trace. So giving me the possibility of having guidance for the software. But yes, I agree, some other fluid dynamical software would be probably a better idea.
Okay, then we have time for 2 more questions. What is the benefit of using a one-dimensional code? Is it computationally efficient?
Well, that's a difficult question. So Trace limits the pipe component to 1D. So there's no possibility of using a 3D calculation.
Mm-hmm. Okay, and then the last question, did you use ideal gas theory to model the air? In other words, did you use a constant heat capacity ratio? Do you think that's a good approach for your application?
So I didn't do that. I don't know what Trace does under the hood. So I didn't do any calculations by hand, so I can't answer that question.
Okay. So thank you, Thomas, and thank you for answering the questions. And then I hand over to Fabio again.
Yeah, thank you very much, Thomas. Next in line, Markus, please share your screen. And please let us dive into the geomatics world.
Yes. So I hope it works. Thank you, Fabio, for the invitation. I welcome you to my little presentation about my master thesis, which I'm currently working on, about the sensing concept for the automated tube installation, especially for the project AlphaTube. I think that we have seen. Then first of all, about me a little bit. I'm not from the ETH. I was born in a very little village in near Bern. I make a first step in the business school, but I quit there and made an apprenticeship as a geomatic expert. After that, I worked for 2 years in this office, and after that, I made my bachelor degree in geomatics at the FNW in Muttenz. At least there at the last 2 years, I worked a lot with remote sensing data, with satellite data, to connect them with deep learning systems or with artificial intelligence to get their data from and to produce new informations out of that. This was a lot of programming and sitting in the warm. After that, I searched a job which I could go on the construction sites, and I find that by a little office in Ordengenbühl, where I worked for the NEAT in the Tunnel Monte There I had to align the railway track of the train. So if you're taking the train from Bellinzona to the Monte and you had to grab your coffee on the table at some point, I'm sorry about that. That was my fault. After that, I worked currently I'm working for the Grundingenieur again in Burgdorf, and aside, I'm on my master degree, also at the FNW in Muttenz, where I'm currently on the master thesis. And about that, I want to tell you some things. First, to the agenda, I will present you some dimensions of the AlphaTube track. I talk about the degrees of freedom we have to use, the parameters we have to measure. Then we talk a little bit about the goals and go over to the concept I have developed until now in my master thesis, and I'll show you a little bit what I currently work on about the test track. The AlphaTube test track, which was primarily in focus, has a length of about 3 kilometers. The route is planed in a municipality of Columbia Mora, a little town or a little village in the valley. Next to the planed route runs the railroad, which allows the individual segments of the draw frame to be delivered. With the use of the railroad cranes, the segments can be lifted and placed in the correct position by an automatic manipulation device. To implement this, a measurement system must continuously measure the difference to the target position and transfer the difference values to the alignment system. The foundations are made in advance. The dimensions of the tube are large and therefore have a weight which causes certain inertia. The construction of a vacuum transport line is comparable to the construction of a railroad line, with the difference that the rails are continuously straightened again and again, and the rails of the tube are continuously straightened again and again, and not as in the railroad construction, the tracks are welded together before straightening, and the placement always takes place in at least 2 rounds instead of 1, which is like planned by this AlphaTube test track. The degrees of freedom, we have 6 of them. I think The two position axes, the two coordinates, always refer to the axis and are in principle detached from the superordinate coordinate system. We have x and y. Those both positions are never or change along the track, the planned track. That means, for example, by a curve, it's always the axis, the x-axis is always the tangent to the curve, to the radius. Then we have the height component, up and down, that are the easy ones. Further, we have the rotations of all the axes. We have around the lateral axis, which represents simply the difference between between the two support points on the foundations. Then we have the critical rotation around the x-axis, also called super elevation, which defines the difference in height between the two rails in the track, like by the building of a railway. And the final one is the rotation around the high axis. That's the simplest one. This is mostly given through the position by the supporting points. Determination of these parameters can be achieved with the following conditions or goals. The determination shall be accurate and precise. Not all devices are able to achieve the listed accuracies, or it requires complex measurements routines or calculations. And with the millimeter, the specifications are already high. The project is also special in terms of precision. The precision is usually defined and controlled by the subordinated network. To do the manufacturing accuracy of the tube, the placement cannot be done by placing the tube itself from outside. But the alignment must be done as close as possible to the exact object we have to place. That's the track or the rails. That means we are in a narrow tunnel, the tube, where we have practically no possibility to control the precision and have to accept distance dependence shifts. Time and accuracy, we have to be fast. Today, the geodetic high precision procedures require time. This can be optimized with the good interaction between the sensor that are used, or with tricks and to take the time out of the variables. With approximately 10 minutes per segment time, I have to say it's a really sporty goal to set one segment of this track. And also the automation to achieve this and to reduce the manpower, the system must directly and in time transfer the difference values to the straightening system on the crane, for example. Out of the railway building, I have those two separate process, the rough positioning and the fine positioning. Both positions have different requirements, which means that different measuring methods and instruments must be used. And soon as the system segment is lifted for the first time, the rough positioning system takes over and places the tube approximately to the position it has to be. To do the lower requirements, influences like atmosphere, time synchronization problems can be ignored, mostly ignored. However, these influences play an important role by the fine placement. Relative to the previously placed segments, the next segment is placed with the requirements that are given to us. In the course of my work, I've looked at different various of possibilities to do those positionings, and now I present you my method I choose to work out. In the selected concept which I present you, two total stations are used for the rough positioning. First, in the time in which the tube segments are delivered, the tachymeter measure the local points to get in the local geodetic coordinate system and by the help of a Helmut transformation calculation. This ensured the implementation of the planning with the surrounding objects and also connect both tachymeter stations with each other. Critical objects around the construction site, like wires, railroads, poles, maybe also buildings, could be integrated in the placement, and this allows that we can, given the system, prohibited zone for the placement where they have to bypass the tube segment. The second step is when the tube is arrived by the train, the two tachymeter lock on targets which are made on the tube and lock on them with the ATR, that's the automatic target recognition system, and do a kinematic measurement with up to 16 hertz. Then the two tachymeter system take over the control of the placement and shift it nearly at the position it has to be. The two tachymeter stations are connected to a calculator unit, which prepares the data and calculated displacement vectors and makes them available for the automatic alignment system. To do the lower accuracy requirements compared to the fine positioning, can a simple mathematical model be applied? Systematic influences only partly taken into account. If the targets are set at different points on the tube, or the straightening device, the super elevation can be roughly aligned with these two targets on different points on the tube. As soon as the tube is in the working range of the fine positioning system, which is placed in the tube, it helps the last centimeters it helps the rough positioning system, the last centimeters to reach, to get in the range of the fine positioning device. The fine positioning system consists of a direct sensor. In my case, it's a tunnel tachymeter with a stable laser, which is located in the installed tube, and two active sensors. As soon we are within the working range, the actually fine alignment is performed. The rough alignment system itself not switched off, but functions as a drift control. The drift reaches to large deviations from the absolute axis. If the range reaches to large deviations from the absolute axis, those measurements and tiered weighted to the difference value calculation, so that the drift can be contracted over the distance and we are getting back on the line. On the last step, we reach the millimeter. We have to consider most influences there. In this step, influences like the time desynchronization of the measurement of the direct finder play a role, as well as the atmospheric influences, which are difficult to measure and to handle and to model. In order to outwit or trick the most influences, we intend to use active targets within the new segment to be placed. The active sensor is an industrial camera which a laser is directed in. The guide laser from the tachymeter is fixed to the target axis given by the placed tube, and the difference to the nominal axis are then detected with the camera by the movement of the laser dot in the camera chip. With this, the time synchronization problems which classically instruments like tachymeter have, and also problems with the atmospheric, can be monitored or completely wished out. If there are no movements on the tube of both tubes and the point have movement on the chip, we have the atmospheric which is in between there, and we could perhaps stop the process, or when it's too great, or take some action. My next step is to build a mini test track where I can analyze especially the fine positioning and to test the individual interfaces and calculation routines I implemented in the last 2 weeks. Unfortunately, the delivery of the material for the construction has been delayed. I would have liked to show you some real pictures already, but in addition, I show you a bit of my drawings about that. In addition, more and surely also still final realizations I will present at the Master Forum of the FN Mutants on the 7th of January next year. And if you are interested in that, feel free to join. I think it's also online this time. If you are interested, tune in and have a look. Yes, that's from my side.
Thank you very much, Markus. Very interesting and also very complex. Thank you for sharing your concepts and your work. Yeah, let's go straight over to the questions. I think there were some raised.
Exactly. So one question is, do you need direct line of sight all the time?
Yes. From both, that's another problem, especially outside the tube. We have to have direct sight to the targets, and maybe, but those system is very dynamically, it could be easily set up on other position.
Okay, then another question is, how much faster could your system be compared to existing solutions?
That's very difficult to look at because of there is no system at the moment which is in real time and which do it automatically. The most systems that are in progress or which worked with it are stop and go systems. So I hope I could be double or triple as fast as the existed process.
Mm-hmm. And the next question is there any heavy computation to be done? You talked about some transformations.
Yes, I have to use transformations, especially to control the drift, which from tube to tube, this drift because of the inside, we work in the inside of the tube is growing. And I have to apply a filter or a calculation to stabilize this drift with the outside measurements. I think I going in the direction of the Kalman filter with that. I implement the art of Kalman filter for that, or I have a simply calculation for network calculation where I widen it the outside measurements really low and bring it in the calculations.
Okay, then we have time for one final question. Could the fine positioning system be used also for underground installation, for example, tubings?
Yes, the fine positioning system could be used easily in underground. The great problem there is, if we are going underground, is the connection to the local subordination coordinate system, like in Switzerland, the LFO 95, because we have no points near them to control also the shift with that.
Okay, thank you very much for answering the questions of the audience. Then I hand back to Fabio.
Good. So last but not least, I'm very happy to also introduce Alfred. He's an industry expert from the tunneling earth tunneling sector, doing some big projects here in Switzerland. Gotthard Basistunnel as one of his bigger projects, and then of course also some bigger and larger infrastructures also in the US. Happy to hear your talk, Alfred.
Okay, thank you so much. Appreciate and welcome everybody to System Risk Management in Action. My name is Alfred Mörgerli. I'm a certificated Swiss civil engineer with a little bit more than 30 years of experience. And although I'm basically a civil engineer, I understand myself more than as a risk manager for high risk environments and especially complex infrastructure projects. You will find more of our documentation on our website, and please feel free to contact me through our email address anytime. So, a quick introduction how it really looks underground. On the right-hand side, Gotthard Base Tunnel. This is from Rohtang Highway Tunnel Project in Himachal Pradesh, India, and Doha, Qatar. And of course, you're not going to become risk managers after this quick talk today. But I'd like to familiarize you a little bit about the basic principles, the first steps, and of course, try to answer the most important, most urgent of your questions today. System risk management in action is a workflow. It starts in situ, looking at your processes, then goes into preliminary hazard analysis, risk assessments, risk response audits, and it comes back to in situ processes, making sure the implemented controls are really working. So what exactly is the added value? We're talking about controlling the effects of your uncertainties, the definition of risks. And of course, we want to stay ahead. We're all looking forward to a safe and happy landing, right? So having a plan B, if something goes outside our controls, staying legally compliant, delivering our cost and time project estimates as planned, and of course, live well with our residual risks at the end of the day. Lots of benefits that come with risk, especially system risk management, but one I prefer myself, I like most, is really higher productivity and safety at lower costs, which is a huge factor for most of us. Let's have a quick look at the very first step, qualitative risk management, starting with risk assessments. Again, we are identifying threats, opportunities, going through risk assessments, planning and implementing solutions, and at the end of the day, make sure our residual risks are now down somewhere into the so-called green arc. So, what are residual risks and when will we be able to accept them? By definition, residual risks are the remaining risks after implementing controls, and we can accept them only, so to speak, if they are identified, evaluated, and assessed, minimized, cannot be minimized more, are well known to everyone, everyone's ready to deal with them, everyone has a fair chance to survive them, and of course, we need to periodically make sure we update and review them. It worked perfectly fine at the Swiss Gotthard Base Tunnel, as you know, still the world's longest infrastructure railway tunnel where I was lucky enough to help our clients CE mark all 4 tunnel boring machines, investments of more than 110 million Swiss francs at that point in time. And it really was the beginning of my personal mantra. If risk management works there, it will deliver value added for you as well. Believe me, everywhere. How to control the top risks of risk management itself. It's all on one page. It starts on the left-hand side. We'll have to identify our hazards, our risks. Then look for potential cause and trigger, and of course the effects. Without understanding these factors, we're not being able to control them. Then we'll go into a very first risk evaluation before mitigation, before controls, and this is bringing us up to the most important part of a qualitative risk assessment, still being on the same page, just moving to the right-hand side, the risk control or mitigation. And as you can see, in most cases, this comes as a package. It's not that you just have one risk and one control measure. You may have one risk, one threat, but you need to come forward with a control package. We'll then go on and do a risk evaluation after implementation of our controls, leading to our residual risks. That's what this is all about. Let's look at project management and system controlling. Why do we talk about that? You're well aware of BER, Berlin Brandenburg, new airport recently opened up for public use just a couple of days ago. And yes, we have a problem there, BER or used, because again, one project overrunning time and cost substantially. And we want to make sure we avoid that for Eurotube. That's what this is exactly all about. So how do we do that? We normally use in quantitative risk assessment, excuse me, I'd like to go back one slide. This. Here we go. We use a value at risk concept. So within a distribution, we preset a certain reliability level, in this case 70%, to, in this case, end up with 5 million, not to be exceeded cost-wise. And of course, the same will apply time-wise for your schedule as well. So this is how we bring in probability information into a cost estimate. And then, of course, we normally do that aggregating base cost if everything goes as planned, adding risks, adding delays, adding operations and maintenance escalation, ending up at total cost of ownership per a defined milestone, and the pre-selected value at risk. And we, of course, will update that as we proceed through our project. We did that recently for the BART Silicon Valley 2 project in California, connecting the Bay Area with San Jose, Silicon Valley's capital city, for a new, probably the most newest, the most urgent construction project in the US. It's about 5 to 8 billion US dollar, and it's currently in the funding stage, where we went through all these stages you just have seen theoretically, conceptually wise, now applied to a real project. There is no way you'll get federal funding in the US without delivering a probability of 80% of not exceeding a certain amount of cost and time. And as you can see, risk loaded and integrate it with your schedule and expected delay cost. So adding escalation, this again ends up at total cost of ownership. And in this case, we even used this model to make a system decision, or to help our owner making a system decision between a large single bore and the traditional subway design. So this is how it really works. This is now when we start controlling our system. We look at the overall safety, at the substantial completion date, at total project cost, giving us, if it's not working as planned, the option of updating our risk assessment, intensifying or adding new controls, and of course, adjusting our project plan for additional time and money. Let's have a quick look at functional system safety, or the control of the reliability and maintainability of your system. Without going into too much details here, of course, you will get a copy of these slides on demand as discussed previously. It all starts on top with a requirement tracking system before really looking at the reliability, availability, maintainability, and safety of your system, enabling you, putting you into a position to plan risk-optimized maintenance. And adding a business continuity management, that part of management that brings your system back into normal operations as soon as possible after an unplanned downtime. So, why use risk-based maintenance? Risk-based maintenance allows you to do as much maintenance as you need for your planned availability, but not more. That's, of course, a time and cost factor. You can see how we use a fault tree analysis to come up with the overall failure probability of a certain structure, in this case per 1 year. And the same thing safety-wise, now looking at potential damage for human beings, now per 1 hour. So this is how it really works. It comes with a couple of pros. Of course, it supports your risk-based decision-making, your maintenance tailored to your risks, risk-based options for your maintenance, applicable to all kinds of your technical systems, with quantitative, auditable results, and it is scalable. Very important. However, it comes with some limitations as well. Of course, it needs technical systems with at least some minimal descriptions. It needs data. It needs a competent team. And of course, as always, the usual suspect, some time and money. We applied that successfully to the world's first train on wheels underground, following a virtual rail, totally software controlled only at the Brenner Base Tunnel near Innsbruck, Austria, just under construction right now. Yes, and this brings me already more or less to our end. I'll skip this one. I'll skip this one for time's sake, and here we are for your questioning.
Thank you very much, Alfred. I think there were some questions coming in. Let's try to stay in time, and yeah, let's get some nice answers to those.
Nice. So let's go to the first question. What is the biggest risk for large infrastructure in Switzerland?
This is a top question. And I would say running over time and over budget in Switzerland. Does that help?
Then the next question is, what is your intuition? Is vacuum transport infrastructure more risky than conventional railway infrastructure?
Another tough question, yeah. I would say vacuum transportation is something very innovative, very new, with a very unfamiliar track record, if any, so far. So this is really kind of flying to Mars, right? So therefore it is, from my point of view, pretty risky. Otherwise, the approach Eurotube is taking, step by step, keeping it as controlled as possible, I would say it's done in Switzerland, which is a very controlled environment most of the time. It is not the mega project. It is still currently a smaller scale project. It should be manageable. However, we'll have that research and development, that innovative part in there. So bringing everything, all these circles together, yes, I would say it's a pretty interesting, and it is a risky project.
Mm-hmm. Okay, thank you. Then the next question, somebody's wondering, how does a project choose a risk management company such as yourself? Is it based on a track record? Otherwise, how do you know if it is reliable?
Yes. Normally, they have their network. They bring you in based on a limited procurement phase. There is public procurement for that. We actually made it twice, once in New York City and once for that Port Silicon Valley 2 projects. These were both internationally, publicly tendered opportunities. And sometimes you need to be in the right place at the right time, as you well know, especially in Switzerland. It's pretty difficult. Yes, it's all reference-based, and at the end of the day, it's services. So it's trying to think ahead, following a structured workflow. It's believing in people, trusting people, and then staying together.
Okay, thank you. Then we have one final question from the audience. How does quantitative risk management work? Is it a Bayesian approach?
It's a Bool's algebra approach, which is not exactly the same as Bayesian, but it is non-traditional, non-purely arithmetic mathematics. And of course, in order to make it converging fast and economic, we need to somehow cut some corners. There are speed up methodologies, speed up modules integrated, but it needs high tech, high sophisticated software. It needs strong computer hardware, and as always, it needs people to know what they're doing. And it is like Thomas somehow mentioned during Q&A today, there's a lot under the hood going on. It's difficult to really figure out what's going on there if you are not able to check the plausibility of your inputs versus your outputs with pretty simple manual approaches yourself. You always need to do that, otherwise you'll never do what the software at the end of the day will tell you.
Okay, thank you very much for answering the questions from the audience.
You're welcome.
Yes, then I hand over back to Fabio.
Yeah, thank you very much, Alfred. Thank you very much also to you guys, Marcus and Thomas. It was very nice to see your work. Yeah, thank you very much to all the rest of the audience to join in. Next time we will have, again, 2 interesting talks, one regarding an axial compressor feasibility study, and the other will deal about a sensor network for communication on vehicles, on Hyperloop vehicles. So yeah, happy to see you next time. Have a great evening, and yeah, have a nice evening.
Goodbye, everyone.
Ciao, zusammen.
Tschüss.
Bye, thank you.